sequence will be reduced from n to some power lambda. And whenever we have this kind of evaluation, this expression divided by n and 1 minus alpha basically will give you the average version of the linear entropy rate. Then you just take the limit and you can compare them.
I lost your story. So what do you want to prove? Could you explain the statement to be proved?
So we want to prove that this average version of the linear entropy rate has a limit. First of all, this is what you can tell from this expression. Means that we first want to prove the existence of the linear entropy rate, and furthermore, we want to evaluate this convergence rate. So basically, we have to prove the limit of this term exists. That's the reason we look at the sum of the probability term, because for this term, if you take log and you divide it by n and 1 minus alpha, and you take limit, exactly you get the definition of the linear entropy rate, right? Okay. So whenever we have the relationship here divided by n and 1 minus alpha, we will have the relationship of the finite of the average version of the linear entropy of length n and length n to the power lambda. Then we have this kind of evaluation. The difference of them is exponential. So we can prove that this sequence indeed is a Cauchy sequence. So by the way, this H alpha of n is just the same as the term here. So we can prove that this sequence is a Cauchy sequence, so it always converges. So the limit must exist. And moreover, because here we have a polynomial convergence rate, so basically by doing typical limit argument, we also have the polynomial convergence rate of the linear entropy rate. So this is what we want to prove. Okay. So in particular, here in our first result, we show the existence of the linear entropy rate for the class of random processes, and also we have a convergence rate. And then the next step is maybe let me first give some remarks on our first result. The first one is that we view the linear entropy rate as the limit of the finite block version. And the second is that if you want to really compute the linear entropy rate of this given process, then this is not very helpful in the sense that the computation of this term will take is very complicated. It will take you exponential time. And the polynomial convergence rate is not fast enough. So we want to have a better convergence rate. And motivated by the result of the Markov of the linear entropy rate of Markov chain, just have this very clean expression. So we want to use the Markov approximation to approximate the original random process and see whether there is a relationship between the linear entropy rate of the Markov approximation sequence and the linear entropy rate of the original sequence. So let me first give you the definition of the Markov approximation of a random process. So basically, if you have a random process Z, you will have a finite dimensional distribution. Then we define the nth order Markov approximation to the original sequence as it has the same n+1 dimensional distribution of the original sequence. You first have n+1 dimensional distribution, and then you construct the sequence as a Markov chain. That is how you approximate the original sequence by a fixed order of Markov chain. Then for a fixed sequence, you will have a sequence of Markov chains to approximate it. Now, what we want to show is that we want to show that the linear entropy rate of the Markov approximating sequence will converge to the linear entropy rate of the original sequence. And because the linear entropy rate of Markov chain has this kind of expression, in order to prove the convergence here, we want to prove the convergence of this term. So basically, we want to prove some convergence of the eigenvalues between two different matrices. But the nth order Markov chain has a transition matrix, and the n+1 order Markov chain has another transition matrix. These two transition matrix have different scale. So the first thing we do, we will upscale the the transition matrix of the mth order Markov chain to have the same dimension as the transition matrix of the n+1 dimension Markov chain. Then you can compare these two matrices with the same dimension, and by evaluating the how close your entries are, you can evaluate the difference between your eigenvalues. So for example, the second order Markov chain with alpha by 2 has the 2 by 2 is of scale 2 by 2, and the third order Markov chain is of course larger, is the 2 to the power 3 by 2 to the power 3. If you want to compare the largest eigenvalue of these two matrices, you can first regard the second order Markov chain as a third order Markov chain, and then you can express the matrix here to be a new matrix that has the same scale of this one. Then you can compare the eigenvalues. And the entries here is just the conditional probability with memory 2. Here is conditional probability of memory 3. So the only difference between them is that their memory is of different lengths. But remember that we consider processes with exponential forgetting property in the sense that when the memories have different lengths, but the first n bits are the same, then they are exponentially close. So basically, after you upscale the matrix here, it will have the same form as this matrix, and those two matrices, the corresponding entries will be very close in the sense that they will be indeed exponentially close. So you have two very close matrices, then you want to, then the largest eigenvalue is continuous with respect to the entries. So you will expect that the difference of the largest eigenvalue will be exponentially small, and this indeed is true. So by doing this, you can get our second main result, which says that under some conditions of the constant in our assumption, then the Rayleigh entropy rate of the Markov approximation will converge exponentially to the Rayleigh entropy rate of the original process. And why this is useful? Because in practice, we have a faster convergence rate. Basically, we have an exponential convergence, which is much faster than the polynomial convergence rate. So it may be useful in practice. Yeah, so here, I think I already mentioned the note here. It is exponential, and we use a new sequence to approximate the original sequence. And also, the third point here to justify that this condition is not very strong in the sense that a lot of channels in practice will satisfy this condition. So for example, the binary symmetric channel with very small crossover probability will satisfy this condition. So this result should be very useful in practice. Okay, so this is the first part of my talk. Is about the Rayleigh entropy rate. And now let's move to the second part, which cares about the continuity of the Rayleigh entropy rate. So in this section, in the second section, we will show that the Rayleigh entropy rate may not converge to the Shannon entropy rate as alpha approaches 1. So first of all, if we don't have a limit version, we consider the finite block Rayleigh entropy. It always converges to the Shannon entropy. And for all the examples such that the Rayleigh entropy rate is known to exist, it always converges to 1. So for example, for IID process, for Markov process, we have just seen before, and also weakly mixing process, we can all these cases have been shown that the Rayleigh entropy rate exists, and they always converges to the Shannon entropy rate as alpha approaches 1. So we may have the following question: is this true in general? In the sense that, is it true that for all ergodic processes, the Rayleigh entropy rate always approaches the Shannon entropy rate as alpha approaches 1? And in this section, we will show that this is not true in general. So basically, we want to construct an ergodic process such that the Rayleigh entropy rate exists, but it doesn't convert to the Shannon entropy rate. So this is our main result in this section. So we show that there is an ergodic process mu such that the Rayleigh entropy rate exists for order alpha bigger than 1. And when alpha is bigger than 1, the radial entropy rate indeed equals to 0. But at the same time, we can show that its Shannon entropy rate is away from 0 in the sense that it is bigger than 1/2. And indeed, this 1/2 can be replaced by some other constant between 0 and 1. And 2 and 3 will imply that when alpha approaches 1 from the positive side, the radial entropy rate will not equal to the Shannon entropy rate. Okay, so our idea of the construction is that we want, in order to, so 2 and 3 are the two most important properties in our, we want to have for our process. So for the first one, if we want to show that the radial entropy rate equals to 0, basically we want to have some realization sequence to have a probability such that this probability will be approximately larger than exponential, in the sense that the probability of the sequence is bigger than or equal to some beta of m, and this beta of m, if you take log and you normalize it by 1/m, it will equal to 0. So it goes to 0 relatively faster instead of exponential convergence rate. And this will imply that H alpha of mu equals to 0. I will show you details later. And secondly, if you want to have a random process whose entropy is relatively large, so intuitively, we want to have the process such that it's almost uniformly distributed, because uniform distribution always gives you the largest entropy. So if we can show that our process is not very far from uniform distribution, then intuitively we can show that the entropy of that process will be not close to 0, so it will be bigger than or equal to some constant. So these two are the two goals we want to have for our target process. And the way of constructing a process to specify these two conditions is the so-called cutting and stacking method. And this method indeed is from the ergodic theory. And it is very useful in constructing stationary processes when you want to control some probabilities. And some applications of this method, although both of them from ergodic theory. The first one is the Austin used this method to prove the celebrated Austin's isomorphism theorem for Bernoulli shifts. So basically shows there that when Bernoulli shifts, two Bernoulli shifts have the same topological entropy, then they're isomorphic. And Paul Shields also used this method to construct various interesting counterexamples. So one of these examples is that he used this method to show that there exist two ergodic processes, such that their divergence rate equal to 0, but they are different. Now, to understand this method, let me first introduce how to have a stationary process in ergodic theory. So basically, in ergodic theory, a process is given by a sample space and a partition and a transformation. Whenever you have a partition of the sample space and the transformation, then you can define your process by x of n evaluated at some sample point equals to a, whenever this n minus 1 transformation of the sample point is in the partition P of A. So basically, how we define the process is we look at the location of the sample point here. Now, the cutting and stacking method, roughly speaking, is that we want to express the sample space as a collection of labeled columns. And then this labeled columns will give you a partition of the sample space. Then we try to define a natural map on this gadget. So from downward to upward, then you have a mapping. But this mapping is not well defined on the top level of the gadget. So it's not defined almost everywhere. So we want to extend it such that it is defined almost everywhere. And the way to extend it is the so-called cutting and stacking method. And finally, you have the partition, you have a map which is defined almost everywhere, then you can define random process. So here is an example. So suppose now this is, all the levels here, the uni is our sample space. And then we express it in a sequence of labeled columns. So here we have in the first column, we have three three layers. They are labeled by 1, 1, 1. And second one is 0, 1, and then 1, 1, 1, and 0. Now we can cut each of the columns and then stack them together. So this red part will be maintained here, but we cut them from 2 columns to 4 columns. And then we want to move this the columns in blue to glue them together with the red one so that we get a new gadget and it is thinner and it's taller. So by doing this, the benefit of doing this is on this expression, the T is not defined on the top level here and here. But if you glue them together, then your T this time will be defined on some of the points here, and previously it's not well defined. So by doing in this way, we can extend our map. So basically, we extend the upper map and the width of the gadget decrease and the height of the height of the gadget increase. And then since every point here is a sample point, by read the labels of the sequence omega, t square omega, t cube omega, then you will have every sample point will give you a realization sequence of the process. Yeah, so basically here is how it goes, and because I don't have enough time, so I'll just skip it. And here is the important thing that we can cut and stack the gadget arbitrarily as long as whenever you want to glue two columns together, they have the same width. Otherwise, you cannot glue them together. So basically, you have a lot of freedom in doing this. And depending on how you carry out the cutting stacking, you may get a process with various properties. So yeah, here is our construction. So remember that we want to have a process such that the probability of 1 is relatively large. So basically, in our construction, we want to have 2 parts. Left part is a sequence of all labeled by 1. Okay, sure. So we want to have left-hand side to have labels all 1 so that the probability of that part will correspond to the probability of the all 1 sequence in the final process. And on the right-hand side, we want the right-hand side, the remaining part to be almost uniform in the sense that it contains all the possible binary sequences and they have the same measure. And then we can cut and stack to get a new gadget. And by doing this, we can always control the gadget on the left-hand side to have a fixed measure. So for any n, we will have a new gadget S of n, which is contained with which contains Lm and Rm, and L of m always has a fixed measure. So eventually we have a sequence of gadgets such that the left-hand side has a fixed measure and the right-hand side is almost uniform. So these 2 properties will imply that our final process has all 1 sequence have a probability bigger than or equal to beta of n, and this will imply that if you consider the Rayleigh entropy range, you have this kind of inequality, which shows that the lim sup of the Rayleigh entropy range will be 0. And on the other hand, since it is almost uniform on most of the sample space, so the Shannon entropy will always be away from 0. So in particular, we will have that the Shannon Rayleigh entropy rate will not convert it to Shannon entropy rate as alpha approaches 1. So basically, we finish the construction. Yeah, thank you. That's all about my talk. Thanks.
So is there any question or comment? Could you show me the definition of ergodic process?
Yes. Any questions?
I'm asking a definition of ergodic process.
Okay. Sorry, I can't hear you clearly. Something wrong with the internet.
Definition of ergodic process.
Okay. Here. definition of the ergodic process. So, okay, so basically, ergodic process means that if you, yeah, so ergodic basically means that if you look at any set in the algebra.
This is definition of ergodic process. Definition.
How important is stationarity?
I'm asking a definition.
Oh, sorry. Can type it in the chat so that I can read it? Because it seems that your sound is not very clear to me.
Hi, he's asking you to state the definition of an ergodic process, and if you could go to the
okay.
slide.
Sure.
We have that.
Sure. I should give the definition of ergodic process here. So basically, ergodic means that if you of course a process is defined on a sample space, on a probability space, right? So if you look at any, maybe let me look at this page. Yeah, here. So in ergodic theory, a process is viewed as you first have a sample space and you have partition and transformation. So basically, you have a transformation for all the sets in the algebra. So the process is ergodic if and only if this transformation is ergodic. And the definition of this transformation is ergodic. Basically means that if you look at any set in this S, its inverse image under T will be the same as itself if and only if the measure of this set equals to 0 or 1. So that basically means that if you want to shift your process, then you will go through all the possibilities of the realization sequence. Yeah. And by the way, ergodicity is very important in proving this.
No, wait, I cannot understand the definition.
Okay. So in ergodic theory, a random process is given by the partition and the transformation, right? So as long as you have a partition and the transformation, you will have a random process, right? And in this case,
this is not the definition, I think.
Of course, you can have various definitions, one from probability theory and another from this ergodic point of view, but I think they are equivalent. So here I'm stating the definition from ergodic theory.
Huh? I'm asking a definition of ergodic process. So this is variant?
Yeah. So any process can be viewed in this way, right? I mean, any ergodic process can be associated with a partition and a transformation, right? And the process is ergodic if and only if this transformation is ergodic. So as long as I can give a definition of the ergodic transformation, then I can use it to define the ergodicity of a random process, right? So this transformation is ergodic if you look at any event in the sigma algebra, the preimage is the same as itself if and only if the measure of that event is 0 or 1. Clear?
No. But we don't have enough time. So
okay.
Thank you very much. So sorry, okay. We need to proceed to the next stop. So thank you.
Okay. So let me stop sharing. Thanks.
So please prepare next speaker.
Hi, yes, I'm the next speaker. Should I share my screen?
Yes.
Can everyone see it?
Yes.
Okay. And next speaker is how to pronounce.
Vyosa.
Vyosa
Vyakai.
Burakhaji. This is the joint talk with Michael Wolf. The title is Can the property of entropy constraint set. So please start.
Thank you. Thank you for the introduction, and thank you, the organizers, for setting up this event. So today I will be talking about a joint work that me and my supervisor, Michael Wolf, have done in transcendental properties of entropy constraint sets. So as a first thing that I want to do here is I want to explain the first word that we have on the title, transcendental. I assume all of us have heard in the past about algebraic numbers, which are basically numbers that are roots of polynomials with integer coefficients. And every number which is not a solution of such a polynomial is said to be transcendental. So such separation, algebraic versus transcendental, not only exists for numbers, but exists also for functions and for sets. And this is basically a tool that we use in our work. And we will call a function algebraic if its graph is basically the solution of some polynomial. And every function which is not a solution of such polynomial then will be called transcendental. And the usual suspects for these functions are usually the exponential and the logarithm, and many other functions. And regarding sets, here comes the word semi-algebraic. So a subset of some real vector space will be called semi-algebraic if can be written as a finite union of polynomial inequalities, basically. So the word semi here is just about the fact that we are using inequalities now here, except equalities, basically. So any set that cannot be written like this is called, again, transcendental. Something else that we will use on this work, and I'll talk about it, are the so-called Nash manifolds and Nash maps. And Nash manifolds are basically just manifolds that are at once smooth and semi-algebraic. And why do I use them here is because I can basically write every semi-algebraic set as a disjoint union of finitely many of Nash manifolds. And Nash maps are defined similarly. They're just maps who are smooth and algebraic basically at the same time. So why do we care about these things, or how are these related to quantum information theory? So basically, this separation between transcendental and semi-algebraic often comes hand in hand with separation between single shot settings and asymptotic settings, or finite theories and infinite theories, basically. So this is the idea behind why we wanted to make use of this in our work also. Before I dive more into our work, I want to talk about the motivation which led us work into these specific sets. So there's catalytic state transformations, which were basically worked by Wilming and co-authors in 2019. So what are these transformations? So for a given density operator rho prime, I want to transform into rho, which is the target state. And I can do this under the following rules. So I can add basically an ancilla state to my initial state, and I can apply a global unitary to my combined state, basically, rho prime tensor sigma. And my final state, which might be correlated, so rho 1, 2 is such that basically in one subsystem, I get the target state, or I get something which is approximately very close basically to my target state. So I denote this by rho 1. And in my other subsystem, I get back sigma, so basically the ancilla state. And this is used basically as a catalyst because it's helping me to perform a transformation, and I get it untouched in the end, which means I can use it for further transformations. So when are these transformations possible? Basically, given rho prime, what is the state of reachable, what is the set, sorry, of the reachable states rho prime, rho, sorry, again. So basically for a given rho prime, I define Sn as the set of reachable states under the constraint that I can use a catalyst of a maximum dimension n. So basically here I just wrote the conditions that I talked previously. And this is just a subset of density operators, basically. And another subset that I will introduce is the set S, which is basically the set of all states that have a bigger von Neumann entropy than the initial state rho prime. We all know the definition of the von Neumann entropy, but I just wrote it here because I'm using the logarithm with the base E. And later on, I will explain that this in the end won't matter, basically the base that I'm using. So there is another observation, which was done by Wilming a year later after the first paper, which basically said that if I take the union of all these Sn sets over n, in the end, I will get the set S, which is basically the set of states which have higher von Neumann entropy than my initial state. So this, in some sense, is the limit when I take n to infinity, which means I don't have any constraints, basically, on my catalyst. And a question which one might ask themselves is whether there exists basically a finite n, which would depend somehow on the dimension of your system, such that these two sets are the same. So maybe we don't have to use an infinite dimensional catalyst. Maybe there is a finite dimensional catalyst that does the job, basically. And how we attach this question is basically this separation between semi-algebraic and transcendental world. And the first observation that we make is basically that the set Sn is semi-algebraic because everything that is defined in the set basically can be written as a polynomial equality or inequality, or a finite union of those. And also here, the fact that we have quantifiers is not a problem, and this is because of a very strong theorem in algebraic geometry, which is known by Tarski-Seidenberg, basically, and says that if you already have a semi-algebraic set, then using quantifiers won't make you leave this world. So you're basically still semi-algebraic. And the other set is the one which was more difficult. And basically, this is a set which has the logarithm on it. And earlier I mentioned that the logarithm is a transcendental function. So basically, this smells like a transcendental set. And if this is the case, then we can clearly see that basically these two sets are not the same. So Sn for a finite n is not equal with S, basically. So the question is, are these sets basically transcendental or not? And in order to answer this question, we came up with a criteria which basically discriminates between semi-algebraic and non-semi-algebraic sets. So basically, the theorem says that if you're coming from an algebraic world, the main two observations here are that basically, analytic continuation of algebraic functions have at most a finite number of branches, or in particular, a compact Riemann surface. And also, if a set is given as a level set of some differentiable function, then the normal space, of this set is particularly easy, basically, to be accessed. And what we do is, in order to answer the previous question, we use the second part of this theorem and try to use the fact that the logarithmic function has an infinite number of branches. Okay, so this is still not yet everything we need to answer this question. So we have to be careful when we consider basically dimensions, because for dimension 2, basically the set of density operators that have fixed von Neumann entropy can be written as the set of states by checking their purity, basically. So this is for qubits, and for qubits, we know that in the block representation, this is just a sphere, and a sphere is very algebraic. So basically, the answer to whether entropy constrained sets are transcendental in dimensions 2, this is negative, because in these dimensions, then these sets are still algebraic or semi-algebraic, basically. When we go in higher dimensions, then things change, basically. And the answer here is yes. And I will try to prove, to present the proof idea by some pictures put in together. So basically, if this one here is the set of states that have fixed entropy, then, okay, this is a manifold. Then I'm applying this map here, which is basically an algebraic diffeomorphism, because I am assuming initially that this manifold here is algebraic. So I'm not changing anything. I'm just parameterizing it into another manifold such that the first d-1 components here are basically the eigenvalues of the operator that I'm considering. What I do next is I take a point basically in my manifold and I consider the normal vector. So this is just the vector which is perpendicular to the tangent space at that specific point. And I can assume that this normal vector has norm 1, so basically is a unit vector. And I can do such assignments to every point on my manifold, basically. So this assignment in some parts of mathematics is known as the Gauss map. And the next thing that I do is I take a path. So this orange curve here, I take a path in my manifold that goes through my point X. And how do I get such a path? So what I do is I intersect an algebraic surface with my manifold in order to get such a path. And I can do the same. Basically, I can just map it to the unit sphere via the Gauss map similarly. Next, what I do is I consider any of the components of my normal vectors here such that they're not constant on my path. And this will give me rise to a function from R to R, basically. And what I do further on is I take this function and I put it in the complex plane. And a technique which is used in complex analysis is analytic continuation. So basically to expand the domain of my function. And when I take the analytic continuation of such function, then I end up with an infinite number of branches. So basically, we all know that when we consider the logarithmic function, this always gives rise to an infinite number of branches or a non-compact Riemann surface, which contradicts my assumption, because if everything was algebraic or semi-algebraic, then these branches would have ended at some point, because algebraic functions have at most a finite number of branches, basically. And this is exactly how the fact that the logarithm is in the definition of the von Neumann entropy gives rise to the transcendental nature of the level sets of the von Neumann entropy. So what did we exactly prove? So we showed that for dimensions greater than 2 and for the entropy values not being extremal, the set of density operators with fixed von Neumann entropy is nowhere semi-algebraic or is everywhere transcendental. So we work locally basically here by always intersecting with an open set in the space of Hermitian D by D matrices. And since we had this result, we thought, okay, what would happen if we would add more constraints basically to such a set, not only having a fixed von Neumann entropy, but some other constraints. And this is what I'll show. Oh, okay, sorry, before I go there, I just mentioned 2 remarks. So basically this statement theorem 2 will hold true for any base of the logarithm, because if I change the base of the logarithm here, that means that I'm just changing the value of C. And also the same result will hold true for if I use, instead of equality here, any of the following inequalities, because from semi-algebraic geometry, then the boundary of a semi-algebraic set still remains semi-algebraic, basically. Okay, so now going back to the additional constraints to the level set of the entropy. So these constraints could be anything from the distance of the state to a specific target, the energy of the state, or the expectation value of any observable, basically. And how do I express these mathematically? So these are described using a differentiable function from the set of D by D positive definite matrices to R. And basically the theorem is quite similar, with the only difference that I'm adding this differentiable function. And I assume also to have a fixed value, basically. And another constraint that we add is that the commutator between rho and the gradient of the function at rho is different from 0. And we do so because we don't want that this is depending entirely on the spectrum of rho. And again, by just using the same proof idea, more or less, that I presented before, we can show that this set is again not semi-algebraic in any neighborhood of the state rho, basically. And as an immediate application of this theorem was basically studying whether the level sets of the quantum relative entropy are semi-algebraic or not. And since basically relative entropy contains in its definition the von Neumann entropy, and this is basically the H function that I talked about earlier. So basically here, I consider any positive definite density matrix sigma. So somehow I'm fixing an arbitrary sigma here and I'm varying over rho. So I fulfill the conditions of my previous theorem. And again, when I intersect in an open subset of the Hermitian D by D matrices, again, following again the same proof idea as before, and using the fact that I can split basically this set R into the intersection of two sets. So one basically being the level set of the entropy and the other as a pre-image of trace or my H function. So I have to be careful here a bit whether the intersection is still a manifold. And similarly, so just extending the proof, we show again that these sets are not semi-algebraic unless the set itself is empty. As a takeaway of this talk, what I wanted to say is basically, oh, was there a question? Sorry.
Okay, please. No problem.
Okay. So basically, the set of reachable states with a finite dimensional catalyst, so with a catalyst at most n, is never equal with the set of density operators that have greater von Neumann entropy than the initial state. So these two initial states that I defined S and Sn are not the same. So basically, there is no universal bound of the dimension of the catalyst that you need to make such transitions. And as a message to take away is that this distinction between single shot asymptotic and finite theories and infinite theories comes often hand in hand with this separation between having something semi-algebraic or having something transcendental. And sometimes we can use these separations for no-go results. So basically that single shot characterization of information theoretic quantities as the one that as catalytic transformation, which was basically that entropies can characterize such transitions only if we consider infinite ancillary systems, basically. And we strongly believe that the variance of the presented arguments here will also apply to many other entropy quantities that appear in classical and quantum information theory. From the proof that I showed earlier, then the level sets, when we consider the von Neumann entropy, are not transcendental. From the proof, you can also see that the same result basically holds true in case you use the classical version. So we're using the Shannon entropy and not the von Neumann entropy. But we believe that also with other entropy measures, we can prove similar results. And with this, basically, this is the end of my talk. And I thank you for your attention, and questions are welcome.
Thank you for a nice talk. Is there any question or comment?
Yes, Mark.
Hi, thanks for your talk. I guess it should be clear, but maybe you could just say it. The same will be true for Renyi entropies and Renyi relative entropies because of the x to the alpha function.
I think as long as we have these logarithms involved in the definitions of our entropies, we have to be a bit careful. If there are no, if we don't have these usual suspects of the transcendental functions, I think almost things become algebraic or semi-algebraic. But as long as we have these involved, I think we have to be careful because things might get transcendental.
Sorry, like,
or maybe
where alpha is not an integer. Shouldn't this be transcendental?
When alpha is not an integer.
Yes.
There are, there are numbers which are not integers and are still algebraic numbers.
Oh, okay.
Yeah. So basically, my plan is to continue and study these other well-known entropy measures like this, or the mutual information, and see whether these things hold there also.
Well, I mean, I guess the Renyi entropy, it's 1/1 minus alpha, and it involves log, trace root of the alpha. And so,
Yeah.
anyway, I guess you'll discover it in your future plan.
Let's hope.
Thank you.
Sure. I think there was another question. I saw a hand raised somewhere.
Other question or comment?
There's a question in the chat.
Yes. It says the separation shows that there is no one-shot characterization for transcendental case. This basically shows that there is no one-shot characterization for entropy measures, which are defined like this and use a finite ancillary system, basically. Because whatever we are comparing this with catalytic transformations, and those are always, so this set Sn was always semi-algebraic for finite ancilla. But if this ancilla is infinite, then this is no longer algebraic, basically, because this is what our problem is showing. Yes, you can use basically the same argument. But I would say that this separation shows there is no one-shot characterization for algebraic, because entropy level sets are transcendental. Does this answer your question? Okay.
Other question or comment? So maybe, thank you very much. So now we want to proceed to the next talk. So next speaker is Geoffrey Wolfer. So please prepare your talk.
Well, can you hear me well? And can you see my slides?
Yes. So the next speaker is Geoffrey Wolfer. The title is Geometric Aspect of Data Processing of Markov Chain. This is joint work with Shun Watanabe. Please start.
Thank you very much for having me. So as mentioned, I will present some joint work with Shun Watanabe, and we'll discuss processing of Markov chains from a geometrical perspective. First, let me give you an introduction. We'll take the perspective of information geometry. So let's once and for all fix a finite space Y, and we will denote the set of all distributions of a Y by P of Y. And we'll view statistical models as submanifolds of P of Y, which is provided with a Riemannian metric called the Fisher metric, as well as a pair of affine connections. This will enable us to parameterize the distribution as we please. Now, in some
Please, please, back. So I cannot understand previous picture. So I already drop out your talk around this picture. So what do you want to do? This is the only
This is for distributions.
Mixture parameter. Okay.
Right.
Okay.
So in a given chart theta, the Fisher information in affine connections can be expressed as follows. And this perspective has had a wide range of applications. Historically, it helped understand higher order efficiency of statistical estimators. It also led to the ideas of information decomposition, projection, and more recently, it helped develop natural gradient algorithms. And what about Markov models? So first, let's fix up some notation with respect to Markov chains. We'll consider an edge set E such that the graph composed of the vertex set Y and the edge set E is strongly connected. And we consider positive functions over E, as well as the subset of irreducible stochastic matrices. Since we're dealing with Markov chains, we will be able to factor the probability of a given trajectory as follows, where mu is an initial distribution and P is a stochastic matrix. The stationary distribution of P will be denoted by pi, and it will be also convenient for us to define Q, the edge measure, that corresponds to the stationary pair probabilities. Give you some motivation on why we should consider geometry for Markov kernels. Recall the exponential tilting of distributions. So for a given distribution and function, I can construct the following exponential family, where each element is multiplied by some exponentiated term, and I have to be careful to rescale in order to normalize to 1. And here kappa will correspond to the Camelon generating function. The dual of this Camelon generating function will govern the large deviation rates. What happens for stochastic matrices? What if I want to apply the same sort of ideas? And each entry of a stochastic matrix is multiplied by some exponentiated term. Here it is still possible to rescale using the following mapping S. But here this rescaling also has to involve not only a scalar rescaling, but also the right Perron-Frobenius eigenvector associated to the matrix P tilde, in order for each row to be normalized. And here also, perhaps surprisingly, the logarithm of the Perron-Frobenius root of a matrix tilde, and it plays the role of the Camelon generating function, and its dual controls the large deviation rates. There have been further developments. So now we've discussed briefly large deviation, but other concepts have been extended to Markov chains, for instance, in information projections. Somewhat more recently, the dually flat structure of the Markov kernels has been established by Nagaoka. We'll briefly discuss this construction. So going back to the world of distributions, we can define the informational divergence between two distributions as follows. And if you want to extend this idea to stochastic processes, what we usually do is we consider observations of the stochastic process up to some time t. And we are taking the divergence between two such sequences of observations, dividing by t and taking the limit. In the Markov case, this limit exists and is given entirely in terms of the transition kernels of the two stochastic matrices under consideration, thereby creating a notion of discrepancy between stochastic matrices. And it's possible using similar arguments to also extend the Fisher metric as well as connections to Markov chains. And one can recover that D is indeed the canonical divergence associated. One could do the opposite and first construct the divergence over kernels and then recover G and the dual affine connections from D. And so these limiting arguments allow us to express the Fisher information metric and dual affine connections with respect to some chart theta as follows, where now the values of the transition matrix and the edge measure appear in this definition. It further allows us to talk about exponential families. We'll say that VE is an exponential family if the logarithm of its one of its elements can be written as such a affine combination, where notice that the GIs now are over pairs of observations, not only one observation. And the rescaling is done using those three terms that correspond to the S mapping mentioned before, right? So these two are the right orthogonal eigenvector. Let me give you a brief example. So the set of all irreducible matrices over some prescribed set, over some prescribed graph YE, forms an E family. And you can see this by rewriting the logarithm of one of its members as follows, where this logarithm here will correspond to the parameter theta ij. Similarly, we can also define mixture families of Markov chains as follows, where here VM will be a mixture family if its edge measure now, so not its transition matrix, can be expressed as the following mixture. And to give an example, a set of all reversible Markov chains, that is, Markov chains that are satisfying the detailed balanced equations, these form both an M family and an E family. This geometric approach has had a lot of applications in recent years. For instance, in parameter estimation, hypothesis testing, local equivalence problems in HMMs, as well as concentration inequalities for Markov chains. Now let's move to data processing. And go back to the distribution setting first and consider a sequence of observation, n observations sampled from some distribution mu IID. And we also consider a randomized function phi, which targets a different space, X. The operational definition of data processing says that we'll apply phi on each of these independent observations. And we will recover another process, which will also be IID, and sampled from the image of mu under this mapping phi. We can compute this image of mu under phi. We can understand it as mu being acted upon by some memoryless channel. And monotonicity of information dictates that two measures can then only be brought closer together by the action of W. One particular operation that one can perform is a lumping, also called a coarse graining. So this is when phi is deterministic and the target space is no larger than the original space. So here we're merging symbols together into a simpler space. Now, going back to Markov chains now, if I observe a trajectory y1 to yn whose dynamics are being governed by some transition matrix P, and I'm here considering a lumping function called kappa, I can rewrite kappa as a partition of the original space y. But if I'm applying kappa on the successive observations sampled according to Markov chain, is the resulting process still Markovian? Well, it is not always Markovian. The Markov property can be lost, but when it is Markovian, we say that P is lumpable, and we denote it by P belonging to the set W kappa. There exists a characterization of matrices which are of Markov chains which are lumpable in terms of their transition matrix. And here's a small example. So if you consider the 3-point space and the 2-point space, and you're lumping together point 1 and point 2 into point 1. So the following matrix here is indeed lumpable. So the two red terms on the second row will sum to 1/2, and the two red terms on the third row will also sum to 1/2. This is also 1/2, which is equal to 1/2. So we can lump this matrix, and this is the result that we obtain. Now, so far we've been discussing about reducing the state space. What about embedding into larger spaces? In the distribution setting, one such operation is called the Markov morphism. And here the operation is described, is understood as the inverse operation of lumping, where each symbol of the original space X is mapped randomly to some other symbol into Y, with the condition that here no two arrows can point to the same point in the space Y. And this enables us to embed families of distributions into larger spaces. Here, for example, is a depiction of us embedding a simplex into over 2 points into the simplex over 3 points. And there is an interesting property that congruent linear embeddings that are linear mappings from Rx to Ry, which are monotonic and which are right inverse of kappa star. So if you're considering this set of mappings, well, these congruent mappings are exactly the Markov morphisms. Now, we wish to extend this idea to all these ideas to Markov chains. So first, the idea of an embedding for some given lumping function kappa from Y to X, we define the kappa compatible Markov embedding as follows. So it takes a transition matrix in the original space, and the resulting matrix in the destination space is defined as the transition matrix of the lumped point, the transition probability of the lumped point, but here we have to multiply by some matrix lambda. And the constraints of lambda are as follows. So first we need some edge compatibility. We need some edge compatibilities in order for this to be interesting. The second requirement is that lambda belongs to the set of positive functions over the edge set. And the third requirement is that lambda verifies the following normalization condition, which is better understood by looking at it from above. So here's one particular lambda, and we can see that it can be written as a block matrix, where each block is either 0 or is a Markov channel. Right, so this helps us understand condition number 3. Here is an example. So consider the weather model, where the probability of the weather of the next day is given by the current day, and transition probabilities as follows. And say we want to construct a more complicated model, where we want to be able to distinguish between types of rains, right? So between shower and thunderstorms. The original P is given as follows, and here is a possible Markov morphism. And below here is the resulting transition matrix when lambda has been applied. We want to mention some related work on conditional models by Libano and Montefort. However, their mappings are different from ours, and so what we will say now is not exactly the same. One particular property of the Markov embeddings I've discussed now is that the trajectory of an embedded chain can be simulated from the original trajectory. What I mean by that is that if you observe x1 to xk, which is sampled according to P, then there exists a randomized mapping, which we can construct, which gives you a new process when applied on the different observations. And this new process is sampled exactly according to lambda star of P, pushed P. An interesting property is preservation of the Fisher metric, of the dual connection, and of the divergence between 2 points. What is more, this mapping lambda star, so Markov embeddings, if at the entry you are providing with a new family, at the at the exit, you will also obtain an E family. However, unlike the distribution setting, the same is not true for an N family. So given an N family, you can break this property by embedding it into a larger space.
So sorry, cannot wait. I cannot put it back. So I cannot understand the meaning of E geodetic affine. What is the meaning of E geodetic affine?
So here I explained. So if you let's say you have an E family VE in the space WX, and you are embedding this E family using the mapping lambda, right? You obtain a different family in the target space. However, this target family will also be an E family. This is a property of Markov embeddings.
I cannot understand. So lambda star to E geodetic curve to E geodetic curve. This is E geodetic affine. Lambda star mapping the any E geodetic curve to E geodetic curve. The image of lambda star of E geodetic curve is E geodetic curve. This is definition.
Yes.
I see. So lambda star preserves the E geodetic curve, but M geodetic curve is not preserved.
That's right. Yes.
Okay.
Right. Is that okay? Yes. Right. So E families are mapped to E families, but M families are not necessarily mapped to M families. Similarly, we can extend the notion of a congruent linear embedding. In order to do so, we first take a larger set. So instead of just lumpable transition matrices, we're talking about now lumpable matrices. And these can be endowed with the structure of a vector space. And we'll say that an embedding is a kappa congruent embedding if it is a linear map from F to F kappa. If it is monotonic. And here is another condition. It has to preserve irreducibility of matrices. And it still has to be a right inverse of kappa star. And the property is that similar to the distribution setting, the kappa congruent embeddings are exactly the kappa compatible Markov embeddings. To give an example, we can go back to the book of Kemeny and Snell in the 80s, where they have their own ideas of what a natural inverse of lumping should be. And they turn these Hudson expansions. And here's their definition. So consider a set of observations from the Markov chain P bar, x1 to xt. And you can consider the sliding window of observations. Right? So first you take the first pair, then you take x2, x3, then x3, x4, etc., etc. This new process will also form a Markov chain. And the state space of this new Markov chain will exactly correspond to the edge set of the original Markov chain. So what we can show is that this particular type of embedding can be encoded as a Markov embedding. However, this is a particular example of an embedding which is not M-geodesic affine. So to go back to your question, here, this particular embedding can map an M family to something which is not an M family. We can also view this as a first-order family of second-order kernels, and these ideas extend to higher order. And finally, I would like to discuss lumpable kernels and their geometry. So a first observation we make is that W kappa is generally not an E family and is generally not an M family. However, there are still many things we can say about it. So let's introduce a P0 bar belonging to a base space, and we'll consider all the matrices in the larger space that are lumping into P0 bar, and we'll denote these by L of P0 bar. It can be shown that LP0 bar forms an M family in the larger space WYE, and that the dimension of this linear family can be understood. A direct application of this observation is through the maximum entropy principle. So if I have my linear family here depicted in red, and I'm projecting points that are stochastic matrices onto this linear family, I know there is a right angle here. But what if I'm taking a particular stochastic matrix, which is defined as follows? So this is the rescaling, stochastic rescaling of some other matrix, delta E, where delta E is defined as having its entries equal to 1 when the transition belongs to E, and 0 when the transition does not belong to E. It is known that this matrix here is the stochastic matrix which generates the Markov chain with maximal entropy, where the entropy rate is defined as follows. And by rewriting the projection of U onto this family L here, we can see that UE corresponds exactly to the matrix with the largest possible entropy, but that lumps with the constraint that it must lump into P0 bar. A different, another family we want to introduce is the following. Now let's introduce some P origin in the set of lumpable Markov chains. And here in the base set, we can see that we can, since this belongs to the lumpable matrices, we can lump it. And so we have kappa star of P origin in the original set. And now there always exists, we can construct it, a Markov embedding that brings this lumped version to the P origin. There always exists such an embedding. And we will denote by J of P origin the image of WXD by this particular embedding. So here on the resulting space, it can correspond, for example, to this line. And we can show that J of P origin forms an E family in WYE, and we can also understand its dimension. And so these two families that we've defined, now I will become clear why it was interesting to define them. So it turns out that the set of all lumpable matrices can be expressed as a disjoint union of the J's, of the family J's, where each origin point is taken belonging to the family L of P0, where we fixed at the beginning some P0 bar. And this allows us to understand the dimension of W kappa as a manifold. And so here is a depiction, right? So the W kappa here can be represented as this foliation. So each point in W kappa can be represented by a combination of an E coordinate and an M coordinate. Here's an application. If I'm fixing some P0 bar in the base space, and now I'm considering 3 points. So P target, P, and P tag defined as follows. So P and P origin are both on LP0 bar, so they're on this line. And P tag belongs to the leaf here, J of P target, P origin. In this case, the following Pythagorean equality holds. And finally, if I have one more minute, I would like briefly to mention an interpretation of data processing and the property of M contraction. So here the assumptions on the mapping and the families are a bit stronger. So now consider a base a base space here, which is an EM family. That is, it is both an E family and an M family. And we are mapping it into some larger space, embedding it into some larger space through the action of Markov morphism, which is E affine and which is also M affine. So not all of them are, but we can construct some of them that are. So this is one particular type. Now, if I'm taking 2 points, P and P tag, in the set of lumpable matrices, and I'm lumping them, and then I'm embedding them again using this embedding lambda star. I'm getting 2 points now that belongs to this family J, right? So what I did is I moved P and P tag, I moved them to this particular J. Now, this operation corresponds exactly to taking the M projection of P onto J here and of P tag onto J here. And what is more, we contracted the divergence from P tag to P. So the divergence from P tag to P is larger than the divergence from this projection to this projection. So thank you very much for listening. I'll take questions if you have.
Thank you very much. Any question or comment? Could you show me that previous picture?
Which picture?
Yes, previous picture.
This one?
Yes. Yes, this one or previous one. So I cannot find. First, yes, there is so many arrows. So there is so many arrows. So no, not this one. Next. Yes, this one. So you have so many arrows in this picture. So are you considering some information processing in this picture?
So here, these operations correspond to processing, yes. So if I have a lumping, it corresponds to just merging symbols together. So if I want to go from P to this kappa star of P, what I'm doing is I'm just merging symbols together. And if I'm embedding here, we know that there is a data processing operation which allows me to do so. So I will just have to introduce a randomized function. And on the trajectory,
so now you consider two kinds of information processing, K star and lambda star. This is correct?
Yes, it's correct.
So in this case, so you originally P prime, so this are mapped to lambda star, K star, P prime. So you are considering that information processing.
Yes.
But I cannot find why you consider that information processing. But this one is only the one term. Somehow, for example, EM algorithm is considering some iterative algorithm. So then this one converges to some point. But this is only the one step. And why we need to consider that kind of information processing?
So this was an example to show that processing by lumping and embedding again can be understood as an M projection.
So why is that kind of information processing important? Why we need to consider that information processing?
So in this case, this was an illustration.
Was in this case?
In this case, this was an illustration. Now, if you want, I can show you an example where this sort of information processing can be interesting.
Can be interesting.
Yes. So if you're familiar with identity testing, for instance. So let's say you have two Markov chains. Let's say you have in your hands the full definition of a transition matrix of a Markov chain, and you're allowed to observe a sample which is according to some Markov chains that you do not know. And you have to distinguish between the case where the reference that you have corresponds to what you observe, or if the two processes are far apart. All right?
Now you are considering this kind of hypothesis testing.
Yeah, this is hypothesis testing.
In order to make this hypothesis testing, that kind of mapping is very useful.
Yes, because of the following reason. So it can. So some of the questions are well understood. For instance, in the symmetric case, where both the unknown transition matrix and the reference one are symmetric. And it's possible to extend it to, for instance, reversible chains by using these transformations that we mentioned. Because we see that using very basic operations, you can always transform a reversible chain into a symmetric one in two different ways. You can do it algebraically by changing the stochastic matrix into a new one, but you can also do it operationally. You can map the observations that you have, and you can construct a new chain from this. So it allows us to extend, for instance, results for symmetric chains to reversible chains. Did I answer the question on why such data processing could be interesting?
But if that information processing can be used for this hypothesis testing, so you need to more clearly formulate the performance of hypothesis testing in this application. There is somehow two kinds of error probability, first error probability and second error probability, and there is somehow you need to define the acceptance region by using this projection, and that by using that information processing. So, but in this description, you do not clearly describe the acceptance region by using that information processing.
So here, okay, we're not using. So here, this testing problem is in the framework of property testing.
Property testing, but even in the case of property testing, you need to clearly define the acceptance region or something. This is not exact testing, I think.
So here, in this type of questions, what you're interested in is in obtaining the sample complexity that will allow us to distinguish between these two cases with high probability.
High probability.
Yes.
High. But you did not explain that successful probability.
I'm sorry?
You did not describe the successful probability.
So what I mean here in this slide is that, let's say you possess an algorithm that can solve the question in the symmetric setting. And for instance, you know that if you observe, let's say, d over epsilon squared observations from an unknown chain, you can assert with high probability whether the process that you observe has been sampled from the reference, or if it has been sampled from some other chain which is far from the reference. Suppose that you possess such algorithm which works for symmetric chains. What you can do is you can use embeddings in order to extend the guarantees in the symmetric case to the reversible case. And what you will have is that the sample complexity will also change. Instead of involving only the number of states, it will involve inversely the minimum stationary probability of the stationary distribution. This can be shown.
Okay. Sorry. Maybe you already spent enough time. So thank you very much.
Thank you very much.
Maybe we can discuss after our session. So we have enough time. So I will arrange a breakout room. So please prepare our final speaker. Final speaker is Paul Gondorf. Where's Paul Gondorf? Nine. Please stop your presentation, Wolfer. So please stop sharing. So please stop sharing. Yeah. Yes. Okay. This is next speaker. Where is? Okay. So the final speaker of this session is Paul Gondorf. The title of the talk is Continuity of Quantum Entropic Quantity via almost convexity. This is joint work with Andreas Blum Angela Capel and Antonio Perez Hernandez. So please start.
Thanks for the introduction. Yeah, as has been already said, this talk is going to be about continuity of quantum entropic quantities via almost convexity. And although my outline doesn't look like it, the talk is going to be divided into two parts. In the first part, I want to talk about our method that we developed. This method turns almost concavity and joint convexity of a divergence into continuity bounds of that divergence on a suitably defined set, and also gives us continuity bounds on derived entropic quantities of that divergence. By that I mean, if one takes the example of the relative entropy, then this would be, for example, the conditional entropy, mutual information, conditional mutual information. The origins of this method lie in a proof by Aliki, Fans, and Winter, where they managed to derive almost tight continuity bounds for the conditional entropy. And Shirokov noticed that a method could be developed out of that proof, and we then lifted this method to the level of divergences. So this will be the first part of my talk, and the second part will be about applications. First of all, the Umigaki relative entropy is sort of a proof of concept. We will derive the best known bounds for these derived entropic quantities, for example, conditional entropy, mutual information, conditional mutual information. Further, we will obtain something that we call divergence bounds, and also a continuity bound for the Umigaki relative entropy itself on a suitably defined set. And then in the second application, we will tackle the Belovkin-Stasevsky entropy. I will end my talk with an outlook and discuss some future work. So first of all, the method. How do we get from almost convexity to continuity bounds? So we start with a divergence, which is an information theoretic measure of difference between two quantum states. We can define this as well on positive semi-definite operators, but I don't want to dive into definitions. So let it just be said that this quantity satisfies the DPI, so a data processing inequality. And what we need for this divergence, or for our method to work, is two additional things. So the first one is joint convexity, and I drop the joint from now on, and almost joint concavity. Joint convexity is pretty self-explanatory. This just means that we have this inequality here. The almost concavity, however, is a little bit more elaborate. We have not a concavity directly, but we have a correction to this concavity. This property is, however, not that strong in itself, because this correction can depend on the states involved. And the only requirement that we have is that this function here that we consider a correction vanishes as we send p to 0 or 1. And hence it is crucial for our method to work, it's crucial that this remainder function is well behaved. And by well behaved, I mean that if we restrict the set of quantum states that we allow for an input, this function reduces drastically and becomes independent of the states involved. At this point, I should mention that everything that we do is on finite dimensional Hilbert spaces. So yeah, just that it is said, yeah. And then when we have these two properties, we can plug them into the ALAF method. We called it almost locally affine method, or ALAF. And this method will then spit out continuity bounds for the abstractions of, for example, the conditional divergence, mutual information, conditional mutual information, which can be understood as just generalizations of the concept of conditional entropy, mutual information, and conditional mutual information for general divergence. There are some ambiguities when defining these quantities. I don't want to dive into them here. Let it just be said that these choices are at some point a little arbitrary, at other points they are not. And if you're interested, you can dive into our paper. We explain a little more why we go, why we are defining these as such. And I will later say some words, but not too many. And further, we derive continuity bounds of the divergence with fixed first or second argument, and these will lead us to the continuity bounds for the divergence itself and something that we call divergence bounds. In the literature, those things have been called continuity bounds, but to omit confusion with this result, we now call it divergence bounds. Okay, and you've seen on this slide that at the heart of our approach lies the ELAF method, and I want to state the theorem, but I need two definitions so I can do that. The first definition is the definition of an almost locally affine function. So take a f to be a real valued function on the convex set S0. Here S of H is the set of quantum states on the Hilbert space H. And then f is called almost locally affine if it satisfies this inequality. So looks locally like an affine function. These corrections here, AF and BF, we require them to be continuous, non-decreasing on 0, 1/2, and they should vanish for p to 0. And also something that is remarkable in comparison to the almost concavity. In this case, these functions are independent of the states involved. So this is a way stronger property than the almost concavity. Further, I want to introduce the perturbed delta invariant subset. This is a generalization of the perturbed or the delta invariant subset of Shirokov. We need this perturbance because these difference operators here, so they are basically just the positivized difference. In this case, it's the positive part of this distance. In the minus case, it's the negative part. They might not be full rank, and this is a problem in our approach because divergences typically exhibit discontinuities if one has an input in the second argument that is not full rank. So let me just dive into the definition here. So we first of all fix the perturbation parameter, then we again take a subset of our quantum states, and then we call it S perturbed delta invariant if for two states in S0 that don't agree, there exists a third state, and it's relevant that for both the plus and minus version, this tau state is the same. So there exists a tau state such that these states, this delta plus minus states created as such, again lie in S0. Okay, and now we're ready to go to state the ELAF theorem. Again, we take a subset of our quantum states that is an S perturbed delta invariant convex subset of these quantum states and contains more than one element. And f an ELAF function, then f is uniformly continuous if this difference, the supremum over this difference is finite. And in that case, for epsilon in 0, 1, we find an upper bound on this difference here, which is a continuity bound that gives us uniform continuity. That might not be obvious from this representation, but EF is created from our original AF and BF functions that are the defining functions, or that are the functions that make F an ELAF function. So they vanish as we send P to 0, and further are non-decreasing, which means this EF max function that we defined here coincides with EF on the interval 0, 1/2. And the reason why we create this function is that we want a function that is actually non-decreasing on the whole interval 0, 1. So we needed to make this definition. And however, because of this non-decreasing property on 0, 1/2, both agree on this interval. And because with P going to 0, EF vanishes, the same thing goes for EF max. So this is actually a continuity bound, although it might not be obvious directly from this presentation. Okay, and now we have the method, so we can come to the applications. And first of all, I want to start with the Umigaki relative entropy. The definition can be seen here again. As I said, we now need two things. The first thing is the joint convexity. This already has been proven several decades ago by Lieb, for example. And the second thing is the new thing, which is almost concavity with a well-behaved remainder function. And this is the result that we obtain. So we take two pairs of quantum states that satisfy this nice kernel inclusion. Otherwise, we would get infinity for our relative entropy. And then we get this inequality where we have here on the right-hand side the almost concave remainder function. And this function is built from the binary entropy, the trace 1 norm difference of rho 1 and rho 2, and this f function. And this f function is sort of a weighted binary entropy, with C1 and C2 being constants depending on the states involved. And they can be understood as kind of weighted means of these states. What is obvious from these constants, or what is already can be seen from this representation of the constants, is that this function has really this nice reduction property, because if you take, for example, sigma j to be sigma k, then we end up with just a trace of rho j here. So this evaluates to 1. Beta 0 is a probability density on R, which means Cj becomes 1, and then the function f becomes 0 for all p. So if we have that C1 and C2 are 1, then the whole function vanishes. And this is also happening if we require that sigma k is the conditioned rho k, and sigma j is the conditioned rho j, as in the case of the conditional entropy, for example. So this is really a well-behaved remainder function. And now with this result in place, we can derive the continuity bounds for conditional entropy, mutual information, conditional mutual information. The first one is the famous result by Andreas Winter and Aliki and Fans, and we recover that. Then the results on mutual information, conditional mutual information, also pre-existed and can be, for example, found in the book by Hayashi. And what we also obtain is a divergence bound, so a bound on the Umegaki relative entropy of rho and sigma. Let it be noted that at this stage, we don't need sigma to be full rank, which is kind of new for these divergence bounds. So m tilde sigma in this equation or inequality is the minimal non-zero eigenvalue of sigma. The only thing that we need is that the kernel of sigma is contained in the kernel of rho. And we further, as I said, or as has been seen on the slides of the method, we further obtain continuity bounds on the divergence with either fixed first or second argument, and by that also a continuity bound on the divergence itself on a suitably defined set. But these formulas are way messier than these nice formulas, and therefore I omitted them. We have several applications for these results. Two of them are already pre-existed, which are the condition for a state to be an approximate quantum Markov chain. The second one is the continuity bound for the relative entropy of entanglement. And then we have two new results in that direction, which is the continuity bound for the Rains information and a bound on the distance between the BS and relative entropy. This is done by a representation of the BS entropy via the Matsumoto map. We can then write it as a relative entropy, and this allows us to use our continuity bound for the relative entropy. Okay, and now we come to the Belavkin-Stasevsky entropy.
Yeah. Could you show me M sigma tilde? So what is the definition of M tilde sigma?
Once again?
M sigma tilde. So you
yeah.
M, yes, this guy. So where is its definition?
The m tilde sigma. So the m tilde sigma is the minimal non-zero eigenvalue of sigma. So you take the spectral decomposition of sigma, and then you just choose the first non-zero eigenvalue of sigma.
Oh, okay. Okay, I understand.
Yeah. Okay. So now I want to come to the Belavkin-Stasevsky entropy, and some of you might not be familiar with the definition of this one, so I've written it down here as well. And for this quantity, no continuity bounds have existed so far, so these things are really new. And we again go along the same lines as with the relative entropy. So we first of all prove almost concavity. The joint convexity has been proven in the literature as well. So we don't dive into that one, but only consider the almost concavity. And we again recover something that is pretty similar to the the case of the relative entropy. However, there are some minor differences. The first difference is that we don't get the trace 1 norm distance of row 1 and row 2 here, but just 1 minus the indicator function. So this guy is 1 if row 1 and row 2 don't agree, and if they agree, then this is 0. And the second thing that is different is that we now get here a Z0, C0 in front of the binary entropy, and this C0 depends on the maximum of the infinity norms of the inverses of sigma 1 and sigma 2. And also the C hat 1, C hat 2 constants have been now changed, have now changed a little. They've become more complicated. Something that I skipped, unfortunately, but should mention here is that sigma in this stage is full rank. We need to require sigma to be full rank, otherwise the proof wouldn't work, and this can be already seen from the fact that C0 depends on the inverses or the infinity norm of the inverse of sigma 1 and sigma 2. So yeah, at this stage, sigma has to be full rank, and not as in the case with the relative entropy where we just needed this kernel inclusion. Now sigma has to really be full rank. Okay, and with this result, we are ready to go to tackle the applications. However, before we go into that, I want to, I've promised some words on defining things like BS conditional entropy or general conditional entropy for a divergence, and there are some ambiguities. And for example, for the BS conditional entropy, one can abstract from the definitions of the conditional entropy via the relative entropy and end up with these two definitions. And we found out in our paper that this guy on the left-hand side is discontinuous on SH, or given an example where this is shown that this is discontinuous, and whilst the guy on the right-hand side is continuous, which is interesting within itself. But we are more interested in the guy on the left-hand side because we have an explicit formula via the partial trace, which allows us to compute this one, whilst the one on the right-hand side is not tractable, not as easily tractable, I would say. I don't want to dive into the definition or the ambiguities that appear in the definition of the BS mutual information, just give you the definition that we used. Let it be noted that this definition is unbounded, which is also kind of surprising, I would say, because in the case of the mutual information, if we use the Omegaki relative entropy, this one is bounded as well. So the BS conditional entropies, either the variational formula or the formula via the partial trace, they are both bounded, but this BS mutual information is not, and it diverges with the logarithm of the minimum of the infinity norms of the inverses of row A and row B. At that stage, these are not real inverses, but the more Penrose pseudo inverses. So we fill every minimal eigenvalue that might be zero, or that is zero, is just ignored, and is when taking the inverse is just set to zero again. And because we have this problem with unboundedness, we define the BS conditional mutual information via the BS conditional entropy instead of the BS mutual information, and we defined it as such. Okay, now we are ready to go because we know what these quantities are, so we can derive continuity bounds for them. And the continuity bounds, unfortunately, look a little uglier, as in the case of the relative entropy. So maybe don't look at them and just consider the order. So if you massage them a little, you will end up with something that is of order m to the power of -1 times square root of epsilon, and the m in this setting is the lower bound on the minimal eigenvalue of rho and sigma. So we take rho and sigmas that are full rank and have not just full rank, but have a bound on their minimal eigenvalue, a lower bound. Yes. One comment maybe, for the divergence bound, we don't require rho to be full rank. We only require sigma to be full rank. And again, m sigma is not, in this case, is the minimal eigenvalue, and not as in the case of the relative entropy the minimal non-zero eigenvalue. In this case, it's really the minimal eigenvalue of sigma. Okay, and we then use these results to derive applications, and similar to the relative entropy, we get continuity bounds for the variational. We get the continuity bounds for the BS entropy of entanglement, the BS range information, and further our almost concave result for the BS entropy allows us also to prove continuity bounds for the variational definition of the BS conditional entropy. Okay, and now I want to come to an outlook, or the outlook and future work. We have strong reasons to believe that the result on the BS entropy is improvable, and namely for two reasons. The first reason is that in the case of rho and sigma commuting, we would expect the bound of the BS and the relative to coincide. This is because in that case, everything becomes classical and we end up with just the relative entropy for both divergences. Hence, we would also expect the almost concave bound to reduce to the same bound. This is not happening with our bound, unfortunately, because we have this C0 in front of the binary entropy. This is giving us a headache. And the second reason is numerics. We've done numerics on the remainder, almost convex remainder term of the BS conditional entropy. And it turns out that the remainder appears to be independent of the minimal eigenvalue. So what you can see here on the right-hand side is on the x-axis, the convex interpolation parameter P, and on the y-axis, the difference here. And we sampled states as well as convex interpolation parameters for different controlled minimal eigenvalues. So the colors correspond to minimal eigenvalues. And as you can see from this graph, varying the minimal eigenvalue, making it smaller, does not affect the convex remainder. And this is not the case for the remainder that we get. So we would expect that there is a remainder function, or one can find a remainder function that is independent of the minimal eigenvalue. Although this guy is discontinuous on the quantum states, and we have to go to positive definite quantum states such that it is continuous. This is kind of a strange behavior. And this is the second thing that we are interested in, understanding the pathologies of the BS. There are several things that don't appear in the case of the relative entropy, that appear in the case of the BS, and we would really like to better understand these pathologies. And at last, apply our method to different divergences. For example, sandwiched Reni or PETS Reni divergence or geometric Reni divergence, and we are already working on that. So my last slide is a summary. I just want to give you a summary of what I talked about. We developed a method called ALAV to derive continuity bounds of entropic quantities. We recover the best known bounds for the relative entropy in addition to new divergence and continuity bounds. And we obtained the first bounds on the BS conditional entropy, BS mutual information, BS conditional mutual information, and divergence and continuity bounds for the BS entropy. Thank you for your attention. I'm happy to answer questions.
Oh, thank you. Thank you. Nice talk. So there is one question in chat.
Okay, yeah.
Does the method also apply to continuity argument based on other distance, say angular distance between states?
The method is very much tailored towards divergences, but if there might be a possibility of adapting it for different distance measures, the crucial part is really these two properties here that we have. So the joint convexity as well as the almost joint concavity. If one can prove those for a general distance measure between states, then the method should be adaptable. So these two properties, but it might take more work.
Thanks. So there is another question. So another question is, will your perturbation by F in convexity include B invex function, star convex function?
Okay. Once again, can you repeat the question, please?
Yes. So this is the first question. So I overlooked the first one. Will your perturbation by F in convexity include B invex function, star convex function? I cannot understand that meaning. So maybe that's why. So how to pronounce sin? So Ajit sin. So he can directly ask this question, I think. So Ajit, どれやこの人? So please ask directly.
I'm sorry, I didn't get the question. Maybe.
So I cannot get. So please, okay. Huh? No.
Paul, the question is in the chat, and
Okay.
it says, "Will your perturbation by F in convexity
Invex functions
include B invex functions and star convex functions?"
You see, you are allowing perturbation by function F. That means nearby functions are considered. Now in star convex, the convexity doesn't go up to the segment, but a part of the segment. So that means it is a star-shaped thing, convexity is there. So similarly for B invex, such things are there. And operational research people consider that, Kaul and Surjit Suneja, for instance.
To be honest, I have no idea. Maybe I misunderstood the question. So your question is if there are restrictions on the F function, am I correct? Or what the restrictions are on the F function for this inequality?
You allowed a perturbation by F in the convexity condition. Didn't you have a function F?
Yeah.
When you wrote the, so that permits you not to take convexity on the whole line segment, but a part of it. And that comes under star convexity to some extent. Okay, thank you. Maybe I'll email you.
Yeah, I think that's a good idea. Thanks for the question.
Thanks. So Mark, do you have a question?
Yeah, I do. I think it was your slide 5. You talked about applications. Okay, slides keep going.
Here.
There we go. Yeah, I was just wondering if you could say more about these the approximate quantum Markov chain application.
So yeah, this is basically we go to, so if one has the conditional mutual information, then for a state to be a quantum Markov chain, we require the BS conditional the conditional mutual information vanishes, right?
Yes.
So, and the idea then is to use the map, the PETS recovery map, and plug that into the. So if one plugs in the BS the PETS recovery of a state into the conditional mutual information, then this vanishes as well, right?
Mm-hmm. Yeah.
And what we do is we have this vanishing property, and we plug in our original state, then massage the conditional mutual information such that, or we didn't do that, this has been previously done, but we redid it. We massage it towards a difference of conditional entropies, and at that point, when we have a difference of conditional entropies in two different states, we will end up with the different conditional entropy of, first of all, the original state, and then the Pet's recovery of the state. And we then use this continuity, or sort of this continuity bound for the conditional entropy to get a condition on, or an upper bound on the conditional mutual information of a state. And by shrinking sort of the continuity bound, we can shrink the conditional mutual information, which gives us then the approximate quantum Markov chain.
Okay.
In the case that the bound is small. This is the basic idea.
Can I ask one more question?
Yeah.
Are you aware of the open conjecture about optimal continuity bound for conditional entropy? Like rather than what you wrote there, it's epsilon log d squared minus 1 plus binary entropy of epsilon. That's a conjecture. Are you aware of that?
Me personally, not.
Oh, okay. Well, I guess my question was if you had any sense whether this method could lead to solving that conjecture, but I guess the answer is no.
As I said, I don't know the conjecture. Maybe if you could send me something on that one,
Yeah,
I can look it up. That would be nice. Thanks.
sure. Thank you.
So thank you for discussion. So do you have any other question or comment? So now I want to close this session. Thank you for nice talks and nice discussion. Thank you very much. So